Okay, man, there we go. Like you know, I'm Joseph Gada. Welcome to my study for understanding some of the lessons of English that I'm going to teach you. So, the lessons of English, like you know, this is about just the mechanical engineering. You can see that in this description just above me, that the lesson will be about the mechanical engineering. So, we studied many things. We studied already the the thermodynamics, we studied the fuels and the combustion, and we studied also some of the properties of the power plant. And yes, so that was very interesting lesson. So now what we are going to study, this is about the steam engine. We already studied some of the points of the steam engines. So yes, the steam engine is you studied the point one and the point two. We studied about the point one that was just about the introduction of what is the steam engine at all and what we are going to study. So the steam engine, this is a reciprocating system in which we are using the fuels and mostly about the combustion of the fuels to release the steam that will be used. So the steam will be also called as the heat energy. So the steam will be released to be converted into the mechanical power or mechanical work. And then because you see at this moment we use the I can take an example about the power plant. The power plant are using the steam engine. So for just converting the steam, the superheated steam into mechanical power, and then the mechanical power will be converted into the electrical energy. So this is about that, and I guess that not only the power plant that are using this type of system, but also the car. So the cars are also using the system of the steam engine for the fact of using the heat energy that will be released and convert that into the mechanical work. So what we are going to study today will be about the modified Rankine cycle. So as you can see, the modified Rankine cycle is just yes, so this is a modified, I would say modified one because we're just using the same properties of the Rankine cycle, but that will be inversely. And that will be because the Rankine cycle is mostly about the internal combustion engine, but for this one, we are going to modify this one. And like they said, yes, it will be represented by just a diagram. So theoretically, indicator diagram for steam engine is shown in figure 5.3. The figure 5.3 is here, and without clearance volume and with clearance volume in figure 5.4. Yes, and you have also the figure 5.4 that will be just with the clearance volume for the steam engine and also without, like they say. So this is about the diagram, and they say that in figure 5.3 clearance volume is 0, and steam at boil pressure enters into the cylinder at point 1 and cut off at point 2. Then the steam expands inside the cylinder isothermally from point 2 to point 3. Point 3 represents atmospheric pressure and the exhaust of the steam occurs at point 4. And below, for example, below the atmospheric pressure, and the point 4 is known as the point of the release. So at the point 4, like they said, they gave an example that it was just below the atmospheric pressure that the exhaust is just release the steam will be exhausted, so that will be released. And the point 4 is known as the point of release, as you can understand. So this is just about I would say the steps, as you can see, for even an internal combustion engine, there is a step at which we the system will receive the fuels and occur the combustion inside of the combustion chamber, and then after the combustion, there the piston will just go down and then that will go up for releasing just the steam at all. The steam that was used for making the mechanical work will be released, and that was just at the point 4, the point of the release, and then after that the cycle will, will start again. So as you can see, there's just a diagram with a lot of precision about this. Like they say, exhaust occurs at constant pressure line 4 to 5. Again, steam enters into the cylinder at point 4, but suddenly pressure increases to point 1. So the system will just wake up again and again. So you can see that here, and there is also some of the formulas here at which you can calculate the work done per cycle with clearance volume and the mean effective pressure with the clearance volume. So with that you can understand many things about how it works. So now let's talk about the actual indicator diagram. Yes, this is shown just in this figure. Uh, So in this diagram, the point 1, 2, 3, 4, and 5 show actual admission pressure, point of cutoff, point of release, and point of closing the exhaust port and starting of compression, and point of opening of admission port respectively. The area of actual indicator diagram is less than the theory, which is called indicator diagram. Yes, as you can see, the figure 5.4 and 5.5 is showing the diagram, and there is also a formula about how to calculate the indicated power of single acting reciprocating steam engine. Yes. And the indicated power also of double acting reciprocating steam engine also. So yes, it is very important to know this one. So now what we are going to study, this is the work on cycle. So the work on cycle is just about the principle of any thermal system like that. For example, the thermal power plants, the steam giants, and the steam also turbines, even also of the internal combustion engines. The Rankine cycle is sometimes referred to, but for the internal combustion engine, this is a reversible Rankine cycle. So this is something that you have to understand. Uh, is sometimes referred to a practical Carnot cycle because when an efficient turbine is used, the GS diagram begins to resemble the Carnot cycle. The main difference is that heat addition and rejection are at constant pressure in the Rankine cycle. Yes, and the isothermal in the theoretical Carnot cycle. Yeah. Yes, and there's some of the difference between all of them. Just about the release, the release. When there is just the release, like they said, or even the addition, the heat addition and the rejection occurs with less, I would say, what they say, the constant pressure in the Rankine cycle. But in the theoretical Carnot cycle, it occurs in isothermal conditions. A pump is used. So this is something that you have to understand. You don't have to be confused about these types of the knowledges because yes, it is not the same. And of course, at a certain moment, this is the same. Like they say, just the fact of when you are just using that when it is just time. This is between the addition and the exhaust of the heat that the two cycles are looking like the same. But when it is time of this, just the two properties of the addition and the release of the heat, at this moment, like they said, the Rankine cycle occurs with the constant pressure, but with the Carnot cycle, like you said, I would say the pressure will of course decrease, but the pressure will be like that. But this is just in the isothermal conditions. Yes. So that means that there is not any temperature like that. So it is not very difficult to understand. A pump is used to pressurize the water received from the condenser. To pump the working fluid through the cycle as the liquid requires a very small fraction of energy needed to transport it. Carnot efficiency is of about 63% compared with the natural efficiency of 42% for a modern coal-fired power station. The working fluid in a Rankine cycle follows a closed loop and is whizzed continuously. Work is required to drive the pump, the working fluid being in its liquid phase at this point. Yes, and by condensing the fluid, the work required by the pump consumes only 1 to 3% of the turbine power and contributes to a much higher efficiency for a real cycle. Yes, that was just something to say about the rocket cycle. I mean that for giving an example for what it becomes a little bit clearer, you have to see the rocket cycle in the use of the train. There's of course a difference when we use the train and when we use the car. The car is using the Carnot cycle and the train is using the one-kind cycle. For the trains, there is not any pressure that will be just needed for releasing the steam. But for the cars, this will occur because, like I said, this is an internal combustion engine, and the steam, of course, has to be released. And this is exerting a certain pressure on the gas like that. And yes, um, but for the train, like you can see, when you can, yeah, when the train is just moving through the, yes, through, is moving at all. At this moment, you can see that there is a lot of steam that is just released from this one. The steam that is released like that doesn't need any pressure for being released. And this is the steam heat energy that is used for what the just I would say the pistons of the trains will move at all and moving the train just in a way like that. So it is like I said to you, this is the Carnot cycle will occur also mostly in the internal combustion engine. For the one kind cycle, this is for the external combustion engine. So you can just see the difference. So now let's study the waste. We are going to study the four processes in the Rankine cycle. As you can see in this document, there is four processes. The first process is just the pumping process. The working fluid is pumped from low pressure to high pressure. As the fluid is a liquid at this stage, the pump requires some small amount of input energy. Yes, because this is a liquid, of course, it is most easier for the system to release the gas than for the no to release the liquid than for the gas because of the fact that the liquid is a little bit more, of course this is heavy, so no need of a lot of pressure for that. So yes, the pumping process, pumping cycle, and the heating process. The high pressure liquid enters the boiler where it is heated at constant pressure by an external heat resource. Its source to become a trisaturated superheated steam. Yes, yes. So this is at this moment that we use. I would say that at that time you don't have to be confused because we refer mostly about the way that the power plant is working. So you don't have to be confused about that. In the power plant, of course, there is just the pumping process. The pumping process, for example, if we use the heat or even no, the water, the I would say the diesel or the gasoline like that. The gasoline will be or the diesel fuel will be just at the liquid phase, and it will be pumped through the just through the cycle for being used. The train also are using maybe there are some of the trains that are using also the gasoline or the diesel fuel. So yes, it is also used for this one. But at this point, just at this moment, we are talking about the power grid system. So don't be confused. And the heating process. So this is at this moment, like they said, uh, that we are just going to heat our liquid for what it will be transformed into the superheated steam or the dry saturated steam. Um, the input energy required can be easily calculated using the Molear diagram. H and S chart or enthalpy entropy chart are so known as steam tables. And the expansion process, the dry saturated or superheated steam expands turbine. This decreases the temperature and pressure of the steam, and some condensation may occur. The output in this process can be easily calculated using the entropy chart or the steam tables. Yes. And there's also the condensation process. The wet vapor then enters the condenser where it is condensed at a constant temperature to become a saturated liquid. Yes. Yes, there is also the condensation process, just in the Rankine cycle. So at this time, this is mostly about the heat, mostly about the heat because the water, mostly about water liquid that we can use that. And the Rankine cycle is also used in the refrigeration cycle, refrigeration system. So at this types of things, we are just using the simple water. And like they said, it will be burnt at the liquid, it will be heated and then transformed into the superheated steam, and then it will expand just in the turbine. This decreases the temperature and pressure of the steam, and some condensation may occur just during the expansion. And then it will be condensed again and reused by the system. And yes, in this one, we can see just how to calculate the work done in the Rankine cycle. There are some of the properties that you have to take into account. You have to take into account the heat supply to water in turbine, the heat, the waste heat in condenser, the work done on the pump, the work done by the turbine. As you can see, there are some of the things can be. This is about the flow diagram of power plant. Yes. So this is the end of our lesson. Tomorrow we are going to study the steam turbine. I mean that will be a very important lesson for us because yes, there will be so many things to study, and yes, then I mean that will be really cool for us to study that. As you know, there's a difference between the steam engine and the steam turbines. The steam engine using the reciprocating uh, and the steam just turbine is using the rotating. So this is a reciprocating. The steam engine is a reciprocating steam, no reciprocating prime mover. And for the steam turbine, this is a rotating prime mover. So they are just using some of the way that they are working is very different because for this one it is directly converted, and for the second one uh, this will be direct, that will work just thanks to the rotation. Like they say, this is a turbine, so this is the rotation and that. So yes, this is the end of our lesson. I will say you just that see you tomorrow for the lesson about the steam turbine. Thank you for listening.